Okay, we finally reached it. Today, we're going to find out who done it in our pathogen murder mystery series. And this concluding episode is going to have a lot of looking at phylogenetic trees and interpreting them. So buckle up. Here we go. Just as a quick recap, remember we had this mystery pathogen. We looked at the read quality for it. We were able to identify the taxonomy, give a hint of who it was from the reads. We were also able to identify a serotype from the reads using serotyper. We assembled and annotated the genome. And once we did that, once we had those contigs and those genes, we started building phylogenetic trees from that. In addition, we took those contigs and we did a taxonomic identification using MASH that showed that it was pointing to the correct taxonomic placement. And we also blasted the 16S ribosomal RNA gene at GenBank, and we're able to see that it was hitting in the same neighborhood too. So as we mentioned earlier, you can't create a phylogenetic tree with just one genome. So in that Bacterial and Viral Bioinformatics Resource Center, we went in and we collected some genomes to compare to our mystery pathogen. And we were taking the story from the outbreak to examine that. Remember that when the outbreak occurred, they looked and saw that whatever this thing was, they knew it was E. coli, but it was different. It wasn't hitting sera that was anywhere close to anything that they'd seen in recent years in Europe. So they knew it was something different. So we collected genomes from what was circulating in Europe at the time, which was the 0157H7 serotype. Another thing that was an indication that it was that is because it had Shiga toxin, and this serotype is often strongly associated with Shiga toxin. So we collected those genomes pre-pandemic and then another group of post-pandemic. And then because serotyping had indicated that it was 0104H4, we also collected genomes that were pre-pandemic and post-pandemic. And then we launched a lot of trees. Ran a series of those trees. These were 500 gene trees when we did the whole genome tree. And remember that that pipeline takes the nucleotide sequence and the protein sequence and aligns them for that many number of genes. And then it concatenates them together and then it builds a tree. So it's a very powerful bioinformatic pipeline. We also ran 16S ribosomal RNA gene trees because I wanted you to look at the difference between a single gene tree and one that's built with a lot of data, really a whole genome sequence tree. So let's look at them. We could either go into the jobs page or I could go up here into my workspace, but I'll go here and look. This shows that it's me logged in. This is my little smiling avatar face. So the first thing I wanted to show you is the 0157H7 in Europe pre-2011 with the mystery genome. So let's look at that. Remember, you highlight the row and then you can click on the view icon. And this is telling me the information about this job, and it gives you a bunch of files. It gives you a scaled vector graph. It gives you a report, which we'll go into. It gives you a NUIC file, which are the instructions for building the tree, which you may have a different software that you like to use for tree building. I also like to use something called Figtree, so you can download that and use that there in different tree formats. And there's even more. If I clicked on detail files, they try to give you absolutely everything you want, but this is the Reader's Digest version of what they think you're most interested in. This time we don't click on the view icon, or we could if we chose that, but I like to click on the view icon here. And this is loading the tree. And these are the 0157H7 genomes prior to 2011. And here's our guy down here at the bottom. Look at the length of this branch. No wonder this thing didn't highlight any of that polyvalent syrup. It's pretty different. There are some fun things you can do with this particular viewer that it's harder to do in other viewers. Remember when I selected all that metadata that I wanted to show on the tree? This is where you can show it. So if I wanted to see the year these things were collected, I click on that and it's showing the collection year. And most of them were 2003. The legend is right up here. It's kind of small, but you can open it on your own computer and see it. Let me point out there are other things that you can do with this is you can see it this way. When I clicked on that A, it's bringing all the leaves, all the external nodes, and making sure that they're all on the same line. And then this is a cladogram. This is useful to be able to see these bootstrap values. Now look up here. Some of these bootstrap values are poor. Some of these are good. If I go back to the phylogram, you see this flat line here? When you see a flat line like that, it tells you that these things are really close and the tree can't differentiate between them. And look, these were all collected in 2003. And let's see where they were collected. Oh, these guys were all in the United Kingdom. So this is probably what was circulating in the United Kingdom at this time, this particular serotype of E. coli getting people sick. So they were sequencing it. And they're so close, you can't tell that they're different. But this guy is clearly different. Remember that this is a breadcrumb. If I go back here, it's going to show me the job. So I click on that and I want to look at this report file. So I view that, and that's where I see actually the scale bar, which gives me an indication of really how many SNPs, what the difference is between this guy and everybody else. What also is good about this particular pipeline is it gives you all the tree statistics. So it tells you this was over 500 genes. You looked at 500 alignments, and it was this many amino acids and this many nucleotides. We'll compare that to a 16S gene, and you can see that this is a lot more powerful because there's a lot more data. So this was the 0157. Let's look at the 0104. And this is pre-2011. So once again, I click on the view icon, and then I want to see that tree. So you can see here, it's rather than in the last one where it was clearly outside, this one, it's deep in there. So it's very close to this particular genome. And if I want to look at the years of that, actually this was collected in 2001. And so that was around at the time. And when they did the first sequence of this and they built the first tree, they realized that it was really close to this. And at that time, that's how they determined that it was 0104H4, because they could see this. Now that there are these bioinformatic pipelines where you can run the reads and see the serotype, now we're able to do that a lot faster than they were able to do it originally. And if we were to click here and go back to the report and view it, we can see that there are statistics on this too. And so this is a lot of data. In 2011, when we have this thing coming, we can see it's closer to the 0104H4. So let's look at it in all the 0104H4 pre and post years. And let's look at that. We view it here. And so you've got this long flat line. And here's our guy right here. And that long flat line indicates that there's very little difference between them. There's so little difference despite all the data that you're looking at, that the tree algorithm can't differentiate between them. When they did the bootstrapping process, it was like, I don't get this all the time. If you wanted to see that as a cladogram, to see that, some of those values are really weak. But you know what? That's okay. because we're just trying to identify a pathogen, and it's not like I'm looking for the ancestor here, because if I go in here and click the collection year, these guys are all from the pandemic. They are all so close together, it can't differentiate between them, and that's fine. This guy is pretty different, and it looks like it's 2014. If anybody's colorblind, I apologize, because some of these colors will be hard to differentiate between. But here's our mystery guy. So I think that we're learning a lot from this. Let's go into the jobs. And then I wanted to look across not just all the 104, but 0157 and 0104. And I have those all years in the mystery. So this is going to be a big tree. So let's view it. And let's view it here. And our mystery guy is in here that's got this function called dynohide when you have a lot. See, we don't necessarily want to see all of those. But here are the 0157 group, and it's a clear differentiation from the 0104 group. And then if we wanted to see the collection year, could look at that. Ooh, that green is painful. What if we wanted to see the isolation country? Oh, that's a little bit nicer to look at. So that's what's kind of cool about this, right? You can color this thing based on whatever metadata you chose to include in this. And if I wanted the host, so these things were either from pigs, humans, cows, or camels. Okay. Anyhow, so there are interesting ways to see the data. But this is showing that there's a strong differentiation between the two serotypes. And we also saw that when we looked at the mystery genome and just the 0157s. When we looked at the 0104s, it was close to some of them. It was close to one in particular of the pre-pandemic year. And then after that, because of all the genomes that were being sequenced, we got to see that there was a lot of data. So let's look at a 16S, and I want to go into here, click on gene tree, because I want to see this guy, the 16S 0104 with the mystery. So I click on that, and this is a gene tree. So it's based on the sequence of this one gene that's 1,500, I think 23 nucleotides long. So where's our mystery? He's right here. And let's see what years we have here. The collection years. So these are all pre-epidemic. Okay, so I'm just going to turn this off actually. And then if I want to see this guy, I can select that so he stands out. So it's a little different from when we were looking at the genome tree, right? Because this is on a big flat thing. And when we were looking at the genome tree with those 500 genes, it wasn't like that at all. But look here. The support value is weak. It's low. All these support values, well, that one's not so bad. The 74 isn't so bad, and the 76. And some of these guys are okay. But this is just telling me there isn't enough data here in this single gene to differentiate between them. So keep that in mind when you're thinking about these things, is you've got to look at the support values and pay attention to things like that. You don't want to draw a bad conclusion from this. And this, it's just saying it's a weak branch support. Also note that this is midpoint rooting. One of the things that this does in the system, the default is midpoint rooting. But if I were to like click on this, and then I could say if this was what I really thought was the ancestral one, I could reroute the tree and show the root here now. And so I could change the tree based on that. So that's just some of the cool stuff. That's why I wanted to show you tree building here, and also for you to be able to view it here. And Remember, I didn't have to put in a single line of code. It's this free resource and I could do everything there. There are some things I think you should pay attention to when you're looking at the trees. And this was that 0157H7 whole genome tree that was pre-2011. And you notice that our mystery was way down at the bottom, way out of there. So one thing you should pay attention to is the branch length. The branch length is telling you the amount of change based on the entire alignment sequences. This is 500 genes, nucleotide, and amino acids, so it's a lot of data. So it's telling you on that particular scale, it's that many changes across that. So pay attention to that. That's an important thing to know. This one was with both the 0157 and the H7, and here is our mystery deeply embedded in the 0104. So pay attention to the root too. Over here on the left, that is an unrooted tree of the same data. And this on the right is the midpoint rooted. And then we looked briefly at when you choose something and say, this is actually the ancestor. I'm rooting the tree based on this. But then you're making an assumption that you know the history. The no rooting makes no assumptions at all. And this one is assuming that everybody is evolving at the same rate. So that's when they're doing midpoint rooting, and that it should be great when you're looking within a species like E. coli. When you're looking more broadly, I don't know, if you're going at higher taxa levels, you have to take that into consideration. So here's the 16S tree, and there's our little mystery pathogen there. Another thing you pay attention to is the confidence values. When you see a confidence value of 4, you're not very confident. So I want you to make comparisons, especially of the confidence values, of the bootstrap values, and who do you believe more, 4 based on 1 gene or 100 based on 500 genes. So this, to me, I have much more confidence that this is the close relative of this guy rather than any of these guys. You should also pay attention to statistics, especially if it's 1 gene compared to 500 genes. And this gives you the information that has been used to do those confidence or bootstrap values. So we've solved our mystery, I think, using the genome sequences. So who actually did it? And I know you all know who did it, but let's look at it. Our investigation, when we put on our Sherlock Holmes hat, E. coli 104H4 was our murderer. Taxonomic classification using Kraken, 2 of the reads, it gave us really strongly Enterobacteriaceae, and then we could see that a lot of those reads hit E. coli. Serotyping using Serotype Finder, that identified it as O104H4, and that was also from reads. After we assembled it, we did taxonomic classification of the contigs using a program called MASH, and that strongly showed that it was O104H4 and certainly that it was E. coli. When we got the gene from that genome and blasted it, the 16S gene, it strongly 100% identity with E. coli. And then when we did phylogenetic trees of O157H7 and O104H4, that isolate was clearly in the group with the O104H4. So this is pretty much where we started, with a single infection turning into many infections. And when it was the single infection and many infections, first it started with the medical community. And then once a problem was realized, public health was called in. And then once we get a genome sequence, we start doing genomics on it. Some might say, oh, you need a specialist to do this. But I hope that I showed you today that you really don't need to pay for a bioinformatician or a specialist that you can do it yourself at the free resources that are out there. Although I know that there are bioinformaticians on staff and stuff, but they can also use these resources too. And the Bacterial and Viral Bioinformatics Resource Center has a command line interface, so those guys could go at it this way. So this is what this webinar series was based on, examining this part of the pandemic. But then there's downstream stuff that the Pathogen Genomic Centers of Excellence are also trying to develop or show you pipelines of, but that'll be in a later series. So you may be curious, how did the epidemic end up? Well, the family in the index case, they all turned out to be okay, except for the 12-year-old boy. He ended up with some kidney functions that were never going to be normal. Nearly 4,000 people were infected across Germany and a lot of France too. In some satellite cases, people who had been in Germany and traveled across Europe, but the primary focus of the epidemic was in Germany. 53 died. 800 developed hemolytic uremic syndrome, which means they could have had kidney failure, but they certainly had impaired kidney function. As they started looking to try to figure out what happened, where it came from, a vegetable source was indicated. First, they thought it was cucumbers, then they thought it was spinach. When they thought it was cucumbers, they destroyed a bunch of crops to keep it from happening. The same thing with other vegetables. But they finally found that it was in sprouts from seeds that had been imported from Egypt. And so the government's destroying all those crops. It caused a lot of damage, not only the people who were getting sick, but to the farmers growing their crops. So public health people, the kind of impact that they make in their work can help all of us. And that's all I've got. So thank you very much. Bye.